never told. I didn't have to do it.
Yeah, linear algebra is really cool because like.
Yeah, no, I went to the thing there and there's like only quite a few people who did it much. And it was literally just hugging posters and just you have to stay there for a while.
I think they capture like quite a lot of
No one knows
things in mathematical physics which are like much more sensitive.
Yeah, cool. Well, today was just a good for example. He gave out solutions so they're online as well. Got it?
Yeah.
I'm writing my notes each month tonight, so I post everything now. We finished the main bulk of the stuff we're doing these now. It's just like I've done stuff we've got. It's all being standard. Yeah. You should be okay with that. It was just sort of defining those bits.
Yeah, we should do it.
Oh, yeah.
Well, I did tell him I wasn't going to tell you that. I just said I was going to do the same. What did you tell him? Yeah. From Hitler, there's your yeah, it's been fine, I think. It's been heavy on revision stuff. Oh, really? So it's not really like you miss stuff, although it is stuff that you probably need to revise. Yeah,
guess what?
Stuff about operators.
I actually played my first game of League for like 2 years last night.
Did you?
Yeah.
Who did you play?
I played Bane.
Where was inspired?
My friends happened to download it on his computer and then it was a really nice computer, so I thought I'd try it out.
It's got a proper
It's a fucking, yeah, it feels great.
I haven't really need to do anything recently because of like uni and stuff.
Yeah.
This week
I can't make a habit of it.
I'm going to be playing so much more now.
Don't do it. Don't do it. No. Not
I was playing like over September.
really. Don't do it. Good prospects.
The more of it we know, the better it gets. So we go through it. Nobody does that. So I think it's like basically it's just definition.
Do you? I should have just done a biology degree, just done a bunch of memorization.
Because it's actually examples and things.
Yeah. start talking and let my mouth just
I think that's the best thing.
Yeah.
I remember in foundations tutorials, like, not pointing fingers at anyone, but some pretty pretentious questions being asked,
Really, oh god.
like, so there are like different types of infinity, like, what, like, I was just like thinking about that all weekend. Leave my mind blank.
Who said that?
I don't know.
Who said that?
No, but it was just that kind of vibe where I feel like,
I have these student staff handouts afternoon first English.
Because it brings
So if anyone wants me to bring this in, I was going to say something you mentioned about like lecture notes being available to everyone for prerequisite modules.
oh yeah, definitely.
Which is a good idea. Apart from that, we can actually sit down for fourth years come fine.
I'll tell you what, I reckon you should have some kind of formal setup for if people do one split in terms of project.
Yeah.
Because like so many of us are doing it, it's like it doesn't really make sense that it's like this weird thing that
There need to be more year 4 modules as well, but obviously that won't help us now.
Well, then that was not a.
What's that?
Still doing
That's why I remember it. I didn't do that on purpose. Like, they don't have any shit again. I remember in one of my foundations, one tutorials, 30, against Grant. Yeah, Grant said, famously, he was like, oh, this talk was quite exciting, I encountered 2 good things. He took the piss out of him for it, but that's about 2 years.
Hold on a bit.
Yeah. Yeah. I encountered 2 good things. So funny.
He won't be in the finite, will he, today? He's not in the finite, that's the
I don't think I will be.
He asked what have I missed, and then I was like, well, you know, you ever went. You catch up.
Alright.
See how well.
Oh, savage.
Some of us for the episode.
Turned up,
Very
and
often.
you know what you've missed.
This is my first year of actually coming to section.
Yeah, exactly. You
Have you
know.
done a 100% record this year?
I was ill one day, but I genuinely dead.
I turned up to every lecture last semester. This semester I'm just one off.
I say last semester, do you mean in year 3?
In year 3.
Okay.
Yeah, what else would I mean?
Well, it's a very different thing to missing them this year.
Yeah.
Yeah.
I think that's my only semester with a 100% track record. Not even close to the other ones. I remember in mechanics, I went to 3 mechanics, 1 lectures.
I was so bad at that. First and second year, like I can't even.
My school used to give out prizes if you had 100% attendance.
Yeah, that's
And we were thinking
such
it
a
just,
non-prize
we think
thing.
it'd just be shitting, but it was like £100
What?
Amazon vouchers
What?
and stuff like that.
Oh my god.
Yeah, it's ridiculous.
We got a trip to like Thorpe Tower.
We just got certificates.
Certificate, yeah.
Well done.
There's a piece of paper.
We had like an end of year assembly, and like if you'd done it, you had to like walk up and go and accept your certificate for
Yeah.
being in school.
Just wouldn't want
Was
to
it the
do
only thing
that.
you ever got 100% in? Attendance.
Pretty
You
sure,
get
yeah.
existing.
We had a prize called the Endeavour Prize that you got like, if you're a little bit But you tried that, you know, so.
Yeah.
But 1 year my tutor awarded it to me as a joke. Like he was a cool guy. I'll take my hat off to him. That's the kind of thing I'd be scared shitless to do as a tutor, because you could get serious trouble for that. Serious trouble for that.
Yeah.
What was it like?
We did one example.
Exercise 3.11.
Wait, for what?
But in the
For
in,
finite.
Oh,
in
yeah,
the solution
yeah,
sheets
yeah.
it's 3.17.
Okay. Did you cover anything new then, or was
No.
it just like a different example?
There's no exercise. That's what it's
No, it's easy.
I think it'll take you. I think it'll take you like half an hour.
I'm gonna come to the book today, so I'll do it while she's like.
Well, I presume we'll spend the first hour just still doing it. So,
Like a 20-minute each.
Okay, so I guess we should begin. Quick recap. Last time you've seen the monotone convergence theorem, and as a corollary of that, we proved the positive linearity of integrals. So we remember again, at the moment we can only integrate non-negative functions, right? We only define the integral for non-negative measurable functions. And for such functions, we proved this monotone convergence theorem. And then for positive numbers, alpha and beta, we proved this linearity. And that's what we've done last time. And now we're going to continue from there. So from these two, we immediately get the following corollary. On any measure space, X sigma mu, if we have a sequence of non-negative measurable functions, then integral of the sum of all the Fn d mu is the same as sum integral Fn d mu. And really this follows immediately from these two. Because if you only let the sum go to some finite k, then this finite sum is an increasing sequence because all the Fn are positive. So if you add more, it increases. And then by linearity, we can pull the sum out for any finite upper bound. And then you just use the monotone convergence theorem, and you get this equation immediately. So this is nice. So when the functions are non-negative, we can always swap series and integrals, just as an immediate corollary. That's really nice. Okay, we continue with the definition. So far, not only could we just integrate non-negative functions, we also can only integrate over the entire space, right? And now we're going to define integrals over a subset of the entire space. So let f be non-negative measurable on a measure space x sigma mu, and take some measurable set E, then we define the integral over E f d mu to be integral characteristic function of E times f. And we integrate that function over the entire space X. So very simple, just make f0 on everything except E, and then integrate that. That's, by definition, that's the integral over E of f. And then from the Riemann integrals, we know that let me just state the lemma, that's easier. So using this definition, we can immediately see the following: x sigma mu, let x sigma mu be a measure space. F from x to 0 infinity be measurable. And let En be a sequence of disjoint sets. Of sigma. And define E to be the union of all the En. So each En is measurable, and because sigma is a sigma algebra, E must be measurable as well. So we can look at the integrals over En and E. And then the claim is we have the following. Then integral E f d mu is the same as sum n equals 1 to infinity integral En f d mu. Okay, so before we had a sequence of functions, and we've seen that you can pull the sum out of the integral. Now we have a sequence of sets, and instead of integrating over the union, we can sum the integrals over the individual sets if the sets are disjoint. Right? So this should be familiar from the Riemann integral. Right? You have this property that if you integrate over different intervals, you can just sum the integrals. And this is the analogous thing for Lebesgue integrals. And the proof of this, again, is very simple. So basically, last time we've done all the hard work by proving the monotone convergence theorem, and now we're just collecting fruits. We're just the proof of all the things now are rather straightforward. So how do we prove this? Well, by definition, this integral is just an integral over chi En times f, right? So really, this sequence of integrals is an integral over a sequence of functions. And because the En are disjoint, and we're taking the union, this sequence is increasing, right? Because we're adding sets En. So it used to be 0, 0 on En, and if you increase n, suddenly it's equal to f there. So this really is an integral over an increasing sequence of functions, so we can just apply the monotone convergence theorem again. Or if you like, we can apply it with corollary. That's the same. So the proof of this is just apply corollary 422 to Fn chi En times F. And then immediately we get this result, because F can be written as the infinite sum of these Fn. Right, so we have this. So now we have two interesting properties about integrals just for free by applying the monotone convergence theorem. Okay, and now that we can integrate over subsets of x, we can look at the following thing. So if we have a non-negative measurable function, any non-negative measurable function f on the measure space X sigma mu defines a new measure let's call it mu f on sigma by just defining mu f of e to be integral over e f d mu. Right, so you just take f, you integrate it with respect to mu, and we call that mu f. And it's really easy to see that this defines a measure again. For example, countable additivity follows from this lemma. So really this mu f is a measure. And then it's also quite clear that if mu of applied to some set E is 0, then mu f of E must be 0 as well. And in fact, one can show that the converse of this statement is also true, which is quite remarkable, right? So this is just a simple thing that you can do, right? You, if someone gives you a function, you integrate it and you get a measure. A new measure, fine, mu f. But and then you have this property, fine. But one can even show that this property implies that there exists a function f such that the new measure can be written as an integral of the old measure. I'm going to write this down, the precise statement. So the converse is also true. And that's theorem 426. It's called the Radon-Nikodym theorem. statement is the following. Let X sigma be a measurable space. If we have two measures, mu and nu, which are sigma finite, and the following implication is true. Mu of E 0 implies nu of E 0 for every E in sigma. Then there exists a non-negative function f such that nu of E is equal to integral over x f integral over E, sorry, f d nu for every E in sigma. So this is really remarkable, right? The only thing we know is that if one measure is 0, then the other measure is 0 as well. And from that, we get the existence of a function such that for every set, one measure can be written as an integral with respect to the other measure. So this is quite an important theorem, and it's very useful in many situations. And this function f has a name. F is called mu density of nu, or sometimes Radon-Nikodym derivative of nu and it's sometimes denoted d nu by d nu. So this doesn't really have to do anything with derivatives, but it's a suggestive notation to write d nu by d mu. Because if you insert that here, then you can cancel out the d mu. Yeah, so whenever you read about Radon-Nikodym derivative, then people mean this function f that you get from this theorem. Practice this a little bit on the problem sheet, just to play around with the existence of this function and to get familiar with this theorem. The proof of this is quite involved, and it's way too long to do in this lecture. So I'll give you a reference. if you're interested in seeing the proof, how this function is actually constructed, the book by Bauer, which is in the reading material, have a look at theorem 17.10, and there you can find the proof. Okay, what's the time? Okay. So the next proposition is basic again. Let x sigma mu be a measure space and f from x to 0 infinity measurable then if the integral of f is 0, the integral of f is 0 if and only if f is 0 almost everywhere. Quick sanity check. What does almost everywhere mean? We defined this in the lecture.
It's where if it doesn't apply, it's only on the null measures.
Yes, precisely. So 0 almost everywhere means the set where f is non-zero is a null set, has measure 0. So that's what this means. And the proof is an exercise. So on the current problem sheet, one exercise is to prove this. And yeah, maybe I'm saying this too often, but remember, only non-negative functions, right? And that's why this is true. Of course, if the function could be negative somewhere, then the integral could be 0 without the function being 0 everywhere, right? If you integrate a sine function, then the integral over one period gives 0, even though the function is non-zero. So this is only true because we're considering only non-negative functions. Okay, the next proposition, let x sigma mu be a measure space. And f and g be measurable functions, non-negative. And assume that f is equal to g almost everywhere. then the integrals of f and g are the same. So again, f equal to g almost everywhere means the set where f is not equal to g has measure 0. And the proposition says that then the integrals of f and g are the same. So intuitively this means if someone gives me a measurable function, I can change the function on a set of measure 0 however I like, and I'm not going to change the integral. And the proof goes like this. So, by assumption, they're equal, f and g are equal almost everywhere. So we can choose a measurable set such that mu of z is equal to 0, and f is equal to g on x minus z. Right, but then we can do the following. We can write integral over x f d mu. This is the same as integral over x minus z f d mu plus integral over z f d mu. So here we're using lemma 4.24 that we've proved earlier, right? If we have two disjoint sets, then adding the integral is the same as integrating over the union. So this is true because of lemma 4.24. And now this is the same as integral x minus z f d mu, because this integral over z is 0 because of this proposition. Because this is the same as, no, wrong. This is the same as integral over x chi characteristic function of z times f d mu. But now this product of chi z and f is 0 almost everywhere, because z has measure 0. So we can apply this proposition to see that this is 0. So the second equality is proposition 428. So now we only have the integral over x minus z. But on that set, f is equal to g. So this is the same as integral x minus z g d mu. And now I can just do every step backwards, and I get the integral of g over x. So this is the same as integral x minus z g d mu plus integral z g d mu, because this integral over z is just 0, and this is the same as integral x g d mu. Right, and now on the left hand side we have integral f over x, and on the right hand side we have integral g. So they must be equal, and that's what we wanted to prove. Are there any questions up to this point? Okay, so if there are no questions, let's continue. So we can make one quick example. So the things we proved today imply, for example, that the integral from 0 to 1 of the characteristic function of the rational numbers with respect to the Lebesgue measure is 0. Quick sanity check. Who can tell me why this is 0? It's still on the blackboard.
Is it 0 almost everywhere?
Yes. Can you explain why? You don't have to. So the measure here is the Lebesgue measure, right? And we've seen that the rational numbers have 0 Lebesgue measure, right? Every countable set has 0, 0 Lebesgue measure. We've seen that in the lecture. And this function here is equal to 1 on the rational numbers and equal to 0 everywhere else. So it's only equal to 1 on a set of measure 0. So this function is 0 almost everywhere with respect to the Lebesgue measure. So we can apply this proposition. It's 0 almost everywhere, so the integral must be 0. So really, yeah. We can now, if you only see this abstract stuff, you might not realize it, but we can now integrate some functions that we couldn't integrate with the Riemann integral, right? In the very first lecture, I talked about some problems that the Riemann integral has, and one of the problems was that this function was not Riemann integrable. And now from all this big bunch of abstract theory, we just get this as a simple corollary. We can integrate this function because the rational numbers are a measurable set. And we can even compute the integral at 0. So this is just sort of to show that we're actually getting somewhere. We can actually collect concrete results. Okay, so this concludes the beginning of section 4. So now the next section is section 4.2. The Lebesgue integral. And in this section we're going to generalize this notion of integrals to functions that could be negative as well. So we start with the definition, 4.31. So this is just notation now. So let x be any set, and take a function from x to the real numbers together with plus minus infinity. Then we define the positive part of f plus of x to be the maximum of f and 0, and the negative part f minus of x to be, and now be careful, this is the maximum of minus f of x and 0. So these are both, the positive part of f and the negative part of f are both positive functions, non-negative functions. So maybe very quickly one picture to illustrate this. If we have a function that looks like this, so if this is f, then the positive part of f, f plus, looks like this: 0, then it's equal to f here, then it's 0 again, then it's equal to f. That's f plus. While the negative part looks like this, it's equal to minus f, where f is negative, then it's 0, then it's equal to minus f again, so it looks like this, and then it's 0 again. And then immediately from the definition, we have that f is equal to f plus minus f minus, and the absolute value of f is equal to f plus plus f minus. Right. Okay, and the next definition is important. So we start with a measurable space, X sigma mu, measure space. And we take a function from X to the extended real line. Of course, we assume that f is measurable, and now note that f is allowed to be negative. Assume that either integral f plus d mu is finite, or integral f minus